In this video, I'll be explaining the process of evaluating integrals of a trigonometric function. These first 6 formulas can be verified by using differentiation. You will notice that the derivative of cosine u is the answer of our integral function here, sine u du. For instance, the derivative of cosine u is simply negative sine u du. And if we take the integration of the resulting derivative, we have the integral of negative sine u du is simply the original function, which is cosine u plus c. Similarly, if we take the derivative of negative cosine u is equivalent to negative times negative sine u du, and that will become positive sine u du. Now, if we take the integral of the derivative, which is sine u du, is simply our original equation here, that is negative cosine u plus c. Note, the same process is true in verifying the remaining formulas, and I want to take you on a challenge to go and try solving if the given formula is true. Now, there are important cases in evaluating integrals of trigonometric functions. But how does the integral of cotangent u du is equivalent to ln sine u plus c? In this video, I will show you the process on arriving this particular answer. Now, the process is to rewrite our function by substituting the equivalent value of cotangent u. By trigonometric identities, cotangent u is equivalent to cosine u over sine u. Then we can say that the cotangent u du is equivalent to the integral of cosine u over sine u du. Now, if we apply the substitution method of integrating this integral, we should select the appropriate integrand of substitution. We cannot let v as a function of cosine u. If we take the derivative of v is dv is equivalent to negative sine u du. If we take the reciprocal of negative sine u, we could not cancel out our remaining denominator here. So we did not assign v as equivalent to cosine u. Hence, we should assign it as v, which is equal to sine u. Now, if we take the derivative of our variable v, that is dv is equivalent to derivative of sine u is cosine u du. Substituting our newly assigned variables, that is the integral of dv all over v. You will notice that dv is simply cosine u du, in which this is our numerator, and our sine u is our v. Then we can evaluate this remaining integral, that is the dv over v, which is the result of natural logarithmic of v. In this case, our v here is sine u plus c. Hence, this is the process on arriving the ln sine u plus c here. Now, this is important to know the process on evaluating these kinds of integral, because you do not need to familiarize this formula. You should familiarize on what is the process on arriving to this answer. Now, in this case, the same process to our previous scenario, in which we rewrite the function using the trigonometric identities, which the equivalent of tan u is simply tan u du is equivalent to the integral of sine u all over cosine u du. And if we let v is equivalent to cosine u, in which the derivative of this one is dv negative sine u du. Then substituting our newly assigned variables, in this case negative dv all over v, there will be a negative constant here, so negative 1. Simply the integral of negative is simply negative. Then the integral of dv over v is the natural logarithmic of v, in which in this case v is cosine u plus c. Now there's also another method that the integral of tan u du is equivalent to ln secant u plus c. This is our ninth equation. Now the process on arriving this answer, now if we take the integral of tan u du is equivalent, that is the integral of tan u secant u all over secant u du. Now this is true since our multiplier did not change our given function, and this is equal to 1. And if we let v is equivalent to secant u, then the derivative of the variable v is dv is equal to secant u tan u du. And rewriting our given function to our newly assigned variables, that is dv all over v, this is dv here, then the integral of dv over v is the natural logarithmic of v, in which v is secant u plus c. We could write our answer in this form, the equivalent integral of tan u du. Now, we have also another case, that is the integral of secant u du is equal to ln secant u plus tan u plus c. Now, the process on arriving this particular answer is to multiply the integral with a multiplier, that is secant u plus tan u all over secant u plus tan u du. And if we distribute secant u to our multiplier, then the given function will become secant squared u plus secant u tan u du all over secant u plus tan u. Now if we let v is equivalent to secant u plus tan u, and taking the derivative of our variable, that is dv is equivalent to the derivative of secant u is secant u tan u plus the derivative of tan u is secant squared u du. Now this is equal, then we can substitute this term as our dv. So in this case, we have the integral of secant u du is equivalent to the integral of dv all over v, which is equal to the natural logarithmic of our v, which is secant u plus tan u plus c. And that is the process on arriving our particular answer of our equation number 10. We have here another scenario that it is said that the integral of cosecant u du is equal to the negative natural logarithmic of cosecant u plus cotangent u plus c. Now the process here is similar to our 10th equation. In this case, the integral of cosecant u du has a multiplier of cosecant u plus cotangent u all over cosecant u plus cotangent u du. Now this is equal to the, now distributing the cosecant u in our numerator, that is the integral of cosecant squared u plus cosecant u cotangent u all over cosecant u plus cotangent u du. Now if we let v is equivalent to cosecant u plus cotangent u, now the derivative of our variable v, that is dv, is equivalent to the derivative of cosecant u is negative cosecant u cotangent u And the derivative of cotangent u is negative cosecant squared u du. And if we take the common term, which is negative 1, then we can express our dv as negative quantity of cosecant u cotangent u plus cosecant squared u du. And this is similar to our numerator. Then we can substitute our newly assigned variable. Then we can say that the integral of dv, this is negative, since because of our negative here, so negative dv over v is simply equal to the negative and natural logarithmic of our v, that is cosecant u plus cotangent u plus c. And that is the process on arriving into our 11th equation. On the next video, I will give you some examples regarding of what I have shown you here. And that will be all, and I'll see you around on our next topic.